Welcome to the Science Center public lecture series given by Harvard science professors. This is the first this year. There's one every month, and I hope you'll come to all of them. And this will be videotaped, and then it will be online, so you'll be able to see it. If you didn't understand one part, you can play it over and over and over again at home in the privacy of your home. Anyhow, there'll be also questions afterwards, so if you have questions afterwards, or you can come up to the microphone, and since it's taped, and ask your question, and then that can go on forever. So I'm Melissa Franklin. I'm just the person who runs the lecture series. But I'm going to introduce Professor Avi Loeb, who is the chairman of the Department of Astrophysics and Astronomy. It just got renamed, so. Is that right?
Astronomy, yeah.
Just astronomy? Oh, sorry. Sorry. It's the Department of Astronomy. And Avi is the chair and also a theorist, so he's not going to do any tricks here with his hands or his feet. But Avi started off in Israel on a farm where he collected eggs. Then doing that for a while, he decided to go to school in philosophy, but quickly turned to physics and got a PhD at a reasonably early age, 24, in plasma physics, in theoretical plasma physics, so not astronomy. He went to the Institute for Advanced Study in Princeton for 5 years and learned astronomy at the same time as doing astronomy, and then came here and became a professor, assistant professor, and quickly became a full professor at Harvard. So Avi has an amazing number of papers. Actually, when I read his CV, I just kind of got sad. Because I have an amazing number of papers too, but I also have an amazing number of collaborators. But 500 papers. I think it's not exact, like it's plus or minus square root of n. And he's worked on an amazing number of topics, and this recent topic that he's going to talk about today is rather new in the past 10 years. But he has worked on many, many topics and been on the forefront of a lot of really of the most interesting work in astrophysics and astronomy in the past 30 years. And he's, has lots of other positions. He's also a professor, a visiting professor in Tel Aviv and at the Weizmann Institute. And he has all kinds of things. He's, he has medals and things. If he wore them all, it would be hard even to walk. But the one thing he has been talking about recently, which is kind of catches your mind, is the idea, imagine the world at room temperature, the universe at room temperature. When the universe is at room temperature, you could just walk around. Apparently it was 15 million years after the Big Bang. So it would be like this. The universe would have a temperature, and it would be sort of like this. Does that seem interesting at all? Oh my God, that's only interesting to me. Well, if you listen to this talk, which is going to be great because I already know him, he's really good, then you will see why that puzzling statement about room temperature may actually be interesting. Okay, Avi Loeb.
Thank you, Melissa, for the kind words. If my mother was in the audience, she would have believed you. So we are all familiar with the Earth. This is the place where emperors and kings got an ego boost by conquering a piece of land on this two-dimensional surface. But there are more planets like this in the visible universe than there are grains of sand in all the beaches on Earth. And the pride of an emperor conquering even the entire Earth is similar to the pride of an ant that hugs a grain of sand in a huge beach. This is fairly ridiculous. right? We live on a two-dimensional surface, and we will get a good sense of modesty if we would open our mind to the third dimension. It's pretty understandable why people are arrogant. It's because they look down to Earth. If you look up, you realize how insignificant you are. So astronomy at a very fundamental level teaches us modesty. But more interestingly, the question is, what is up there? And I very often, almost every night, step out to the porch and look up at the sky. When it's not cloudy, I see the stars of the Milky Way galaxy. And they look just like lights in a giant spaceship sailing through space. And I wonder to myself, are there other passengers near the other lights in this spaceship? And then when I get back inside, I tell my wife of my thoughts, and she says, well, if there are ETs out there and they ever come to get you, just make sure that you leave the car keys with me and tell them not to ruin the lawn in our backyard when they lift off. So the basic question is, are we alone, or is the universe teeming with life? And that's a fundamental question, and the answer to this question will change our society and our culture if we only knew that answer. So far, my colleagues, some of which are in the audience, assume that the universe is full of lifeless galaxies, lifeless objects. They simulate the formation of structure in the universe, assuming that there is no life. But this is an opening for a new Copernican revolution. Copernicus discovered that the Earth is not at the center of the solar system, like many other people thought at the time. And we might not be at the center of the biological universe, as we are thinking right now. So a lot of people prefer to think that we are very special. Perhaps there is no life elsewhere, or at least there is no intelligent life elsewhere. Some of us are wondering if there is intelligent life here, but that's a separate matter. So let me explain what astronomers are talking about when they mention life. It has a very specific context. For astronomers, life is associated with chemical reactions in liquid water, just like life here on Earth, which produce gases like oxygen or methane at abundances that are vastly out of equilibrium. So this is a good definition, because then you can go out and search for these abundances in the atmospheres of planets. Intelligent life is defined as a form of life that produces artificial signals which are highly improbable under natural circumstances. So if we see something completely unusual on the sky that we cannot really explain through the laws of physics under natural circumstances, that would be alarming. There could be life out there. And the search for life more generally, and that's a statement for any dean that is in the audience, is the ultimate interdisciplinary frontier, because it involves astronomy, obviously, we are looking at the sky. It involves planetary science, because life as we know it exists on the surface of planets. It involves chemistry. You have to get these reactions going in order to get life. It involves biology, statistics, if you want to estimate the likelihood of seeing life in different circumstances, physics, obviously, mathematics, and engineering. And it has implications for sociology. It will definitely affect our society if we find life elsewhere. It will affect economics, government, philosophy, psychology, linguistics, because we might want to communicate with these other civilizations, art, there are lots of movies already on extraterrestrials, history, our sense of our history and the history of the universe will change, and theology. For some people, it will have implications for their religious beliefs, because if we find intelligent beings elsewhere, you have to reinterpret the Bible or other texts that you believe in. So talking about biology far from the Earth has different regimes, and we can split it based on the distance scale. We can start with the solar system and ask whether there is evidence for life in the solar system. And that involves, for example, whether there was liquid water on the surface of Mars, which is a question being addressed right now. Whether there is bacteria on Enceladus, a satellite of Saturn, or fish on Europa, a satellite of Jupiter. Under the ice, people believe there is liquid water, and the question is whether there is fish swimming there. And in principle, these places are places we can visit. But once we go beyond the solar system, it will be difficult to visit those systems on a human lifetime. So an interesting question is whether there is life in other planetary systems, extrasolar planets. And this is the basis for a completely new frontier right now called astrobiology. It's a mix between astronomy and biology, and there are journals already publishing papers on astrobiology. Then you can go beyond the vicinity of the sun and consider intelligent life in the galaxy, and that could lead to a completely new field of study which doesn't exist. There are no journals on this one. A combination of astronomy and psychology. How do other intelligent beings think, and how do we communicate with them? And then you can go to the cosmological context. When did life start in the universe? And when will it end? And I will try to touch on these questions in my lecture. We obviously don't have a clear answer at the moment. And I termed this frontier, which actually is just starting. It started earlier this year when I wrote the first paper on whether life was possible at early cosmic times. And I called it cosmobiology or biocosmology. So let me describe various techniques that astronomers are thinking about in the context of searching for life at these different distance scales. And a simple exercise that I did last summer was to check what if there is a nuclear explosion, a nuclear war in a civilization on one of the nearest stars next to us. Will we be able to see it with modern telescopes? And the answer is that even the bright flash from a nuclear war on a planet around the nearest stars to the solar system would not be detectable by our largest telescopes. So let me start from closer distances, the solar system. And as you well know, there are planets orbiting the sun in nearly circular orbits, but then at a distance that is roughly 100 times the distance of the Earth from the sun, there is a collection of objects called the Kuiper belt objects that are just relatively small objects orbiting around the sun. And Pluto is one of them. That's why some people demoted it as being a planet. But now we know of many more objects, not very different from Pluto. So could these objects have intelligent life on them? And one way to find out is to search for artificial light on such objects. So all astronomers, other than me, think that the objects in the solar system are being illuminated by the sun. and we are just seeing the reflected light. But what if there was artificial light produced on one of these objects? Could we tell the difference? The answer is yes, because if you have an object that is illuminated by the sun, the flux that is impinging on the surface of this object declines as 1 over the distance of this object from the sun squared. But then we see a flux that has another power of 1 over distance squared because this object is far from us. So altogether, combined, there is a dependence on 1 over distance to the 4th relative to us when we are close to the sun, much closer to the sun than the object we are looking at. This is quite different from an object that has been producing artificial light, because in that case, you have just one factor of 1 over distance squared. So if you see an object moving away from us, you just need to monitor the flux of this object and see whether it follows a scaling with 1 over distance to the 4th or 1 over distance squared. Very simple. When I asked one of the discoverers, one of the most prolific discoverers of Kuiper belt objects, why isn't he checking whether their flux falls off as 1 over distance squared or 1 over distance to the 4th? He said, it's obvious. It must be 1 over distance squared. What else? What could it be other than that? And the problem is that people often assume the answer before they check it. And I actually wrote an essay on this, illustrating with 10 examples how people, astronomers in particular, thought that they knew the truth before they looked at the sky, and they were wrong. One of the famous examples is the first PhD in astronomy at Harvard Radcliffe, written by Cecilia Payne-Kopashkin. She concluded by examining the spectrum of the sun that the sun is made mostly of hydrogen. But at the time, people thought that the sun has the same composition as the Earth. And so Henry Norris Russell, a very famous, prominent astronomer, the director of the observatory at Princeton, convinced her to take out this conclusion from her thesis. He said it doesn't make sense, and then he tried to show that she was wrong several years later and figured out that she was right. So the mistake that astronomers make, and that's a signature of a field that is starving for data, the mistake that people often make is a shortcut. They think they know the answer, and they don't have enough modesty to admit that they can live with the uncertainty of not knowing the answer. And in the context of looking at these Kuiper belt objects, if you, for example, place a city like Tokyo on one of these objects, you should be able to see it with our best telescopes. For the astronomers in the audience, Tokyo is a 31st magnitude source at 1,000 astronomical units, 1,000 times the distance of the Earth from the sun. And of course, if you think about the history of science, it was common sense to think that heavy objects fall faster than light objects until Galileo tested it experimentally. So we should, if we have the ability, and if it doesn't cost extra resources, we should simply check the assumptions that we make rather than assume them, especially in the context of searching for life. But let's go back to nearby stars, because that's where the likelihood could be higher. And one way to search for extraterrestrial intelligence that by now has a name, SETI, searching for extraterrestrial intelligence, is by searching for signals. And back in the late 1940s, Enrico Fermi, a very famous physicist, reached a very deep conclusion. He said, well, if there are intelligent civilizations out there, where is everybody? We should see them around. We don't see anything. They should have visited us. We should have seen evidence for it on the surface of the Earth or everywhere in the sky. Where is everybody? The fact that we don't see anything with our naked eyes perhaps tells us that we are rare in the universe. And that's a very good question. He didn't write a paper. He just asked this question. And Still, 74 years later, we don't have the answer. So one conclusion you can draw, well, if we don't see them, they don't exist. But some other people said, well, let's go and search more carefully. And in particular, in 1959, there was a Nature paper written by Cocconi and Morrison, where they stated that the probability of success is difficult to estimate. But if we never search, the chance of success is 0. And I actually checked with one of the most prominent statisticians who is sitting in the audience, Xiaoli Meng, who confirmed that indeed this statement is correct. In 1960, before most of the audience was born, the first SETI took place with a 26-meter radio telescope by Frank Drake, who was a graduate of the Harvard Astronomy Department. In fact, I was corresponding with his daughter yesterday. She is a science reporter for National Geographic. So that's an interesting connection. And subsequently, obviously, the first experiment was to look at 2 stars and check, because it was not known back then, whether any star has radio signals coming off it, just like the radio signals we are producing. So they checked 2 stars, they didn't find anything. And then there were many other projects following on that. HRMS in NASA, a sequence of projects at Berkeley, and then some here at Harvard. The Paul Horwitz from the physics department pioneered some search techniques, including optical SETI, searching for laser signals from other civilizations. But nothing was found. And then in 1981, SETI was removed from the NASA funding by the US Congress. And this is the dish that was used, the 26-meter radio telescope at Green Bank that was used by Frank Drake back in 1960 to look at 2 stars. Found no signal whatsoever. Today, we have much better radio telescopes. The most advanced ones at low frequencies were constructed to search for signatures of the first stars in the universe by mapping hydrogen at early cosmic time. So one is trying to detect the feeble radio signal from hydrogen that was actually first detected by Ed Purcell from his office window in the physics department here at Harvard. He detected the signal from hydrogen in the Milky Way galaxy. Now we are aiming to detect this signal from the entire universe and map the distribution of hydrogen in it. And then the first stars that formed in the universe produced regions where hydrogen was broken into its constituent electrons and protons. And so we should see bubbles, evidence for bubbles of destroyed hydrogen around the very first galaxies. So that's the goal of this frontier. And arrays of radio antenna like this one were built, one of which is in Western Australia. That's the one shown here. But there are others, one in Europe and another one in Africa. And now, in principle, we can use those to also constrain radio signals from other civilizations. So what the observers showed when these arrays came into existence is that if you are putting the array close to a city like Sydney, you get a very strong interference signal from all the radio and TV broadcasting in this major city. But if you go far to the Australian desert, then the signal goes away. And so when they showed it at one of the conferences, I wondered to myself, well, maybe we can search for these signals from other stars. And then we wrote a paper with Matthias Zaldarriaga illustrating that, in fact, these arrays that are being constructed now will be sensitive to the signal that Earth is producing out to distances of order 50 light years. And that's interesting because we have been broadcasting for more than 50 years. So in principle, if there is a civilization out there that builds the same arrays that we are building now, they should be able to see us. There is a bubble of radio waves that is moving away from us at the speed of light, and it has roughly a radius of 50 light years, because we started transmitting around that time, 50 years ago. And actually, the strongest signal that our civilization produced was due to ballistic missile early warning system. Back during the Cold War, there were these huge radio transmitters aiming to detect ballistic missiles. But of course, most of the time they were broadcasting into space. And since most of the radio power on Earth was transmitted for military purposes, we better not respond to the brightest extraterrestrial civilizations that we ever find, because they might be militant. But a more interesting question is, what do we do if we detect a signal? And for example, as a scientist, I would like to find answers to some very deep questions. We could ask the extraterrestrial civilizations, what is the nature of the dark matter and dark energy, for example? These are questions for which we don't have the answer right now, but if these civilizations existed for billions of years, they would know. In a way, that would feel like cheating in an exam. And there are two versions of this. One is the secular version, where you see a student copying from another student during an exam. But there is also the religious version, where there is a supervisor looking over their shoulder. So whatever camp you belong to, it would feel like cheating in an exam. Let me mention other techniques that are being discussed right now and that are much newer. One of them has to do with trying to detect the light from a planet next to a star. And the biggest problem is that a star like the Sun is 10 billion times brighter than a planet like the Earth. So you get blinded by the light coming from the star. But if you build something that looks like this, a star shade that has very specific shape, you can block the light from the star and get a very dark region around the star such that you will be able to detect the planet. If you were to use just a circular aperture, you would get diffraction patterns. And the leakage of light can go around the obstacle, just like water goes around an obstacle in a pond. And so you get too much light if you were to just use a circular aperture. But if you use a very specially designed aperture, you can remove the light to much larger distances so it doesn't bother you near the center where you are trying to find evidence for the planets. And NASA is now funding an effort to develop this nice aperture that opens up in space and is tens of thousands of miles away from the telescope that is looking at the star. And the hope is that with one of the upcoming telescopes, like W1 this star shade will allow us to reach the contrast of 10 billion. A contrast of 1 billion was demonstrated already in the laboratory. An alternative would be to use a coronagraph, which is the same general idea, but having the mask inside your telescope. Now, we shouldn't assume that all the planets would be habitable at the same distance from their host star as the Earth is relative to the Sun. Because if you have a star that is brighter than the Sun or more massive than the Sun, then you want to position the planet at a greater distance. It's just like being next to a furnace. If you want to keep yourself warm but not get burned, then there is an optimal distance where it's not too hot and not too cold. In this case, for liquid water to exist on the surface of the planet. And that's called the habitable zone. And as you make the star more massive or brighter, the habitable zone goes farther away from the star. And obviously, you want it to be around the distance of the Earth from the sun for a star like the sun, because this is the only example that we know of where life exists. And one of the graduate students in the astronomy department is finishing a PhD on the atmospheric composition of planets around different types of stars. Sarah Rugheimer. How can you detect the composition of the atmosphere of the planet? One way to do it is by looking at the planet as it orbits the star, and if it happens to pass in front of the star, then a fraction of the light of the star is passing through the atmosphere of the planet, and then you can take a spectrum of that, basically a prism that splits the light into different colors, and look for the fingerprints, the spectroscopic fingerprints of the different molecules that make up the atmosphere of the planet. So the idea is to look for transiting planets and search for evidence for these absorbing molecules in the atmosphere of the planet as light from the star is passing through the atmosphere on its way to us. And that's pretty difficult for a planet like the Earth orbiting a star like the sun, because the Earth is 100 times smaller than the sun. And so it covers only a percent of the area of the sun. And so if you can't resolve the object and you're just looking for the spectral fingerprint, it would be very tiny because most of the light doesn't really pass through the atmosphere of the planet. So it's very challenging to do this, even with the next generation of telescopes, for a planet like the Earth around a star like the sun. But what you would like to do is search for molecules like oxygen, because molecular oxygen would disappear from the atmosphere of the Earth if life ceased within 1 million years or so. So the existence of oxygen in our atmosphere is a clear evidence for life. It's some 20 orders of magnitude more than you would expect in chemical equilibrium. If you have oxygen and methane together, you can establish that the abundances of these molecules is way out of equilibrium. And so the first thing we need to find are planets that are transiting in front of their stars. And in fact, the Kepler satellite found more than 3,500 candidates for such planets by monitoring very carefully the light from a lot of stars and looking for a dip whenever a planet passes in front of the star. And there is a planned satellite to be launched in 2017 that is currently being designed at MIT and Harvard that is called TESS. And its purpose would be to monitor 500,000 stars over 2 years. And it will be sensitive to Earth-sized planets in the habitable zone of dwarf stars, stars that are smaller than the sun. So that would be quite exciting. From Kepler, we already have 800 or so planets that were confirmed. So not only there was suggesting evidence that that there is a planet passing in front of the star by seeing the deficit in the flux of the star, but people were able to actually measure also the gravitational tug that the planet exerts on the star as it moves it back and forth when it moves around it. And so that confirmed the existence of these 800 planets. And you can see here that most of the planets were discovered recently, a lot of them, or a substantial fraction of them. Now, based on the Kepler data, we are able to infer what is the fraction of planets that have roughly the size of the Earth in the habitable zone of their host star. And the first paper to address that was by Courtney Dressing, who is a student in the astronomy department at Harvard, supervised by Dave Charbonneau. Over a year and a half ago, they figured that about 15% of dwarf stars in the Kepler catalog have roughly Earth-sized planets in the habitable zone of these stars. And then more recently, there was another study by Jeff Marcy and collaborators that inferred that 11% of sun-like stars have roughly an Earth-sized planet that is warmed by roughly the solar flux, so making it close to the habitable zone. So these are significant abundances. Because we know that there are 300 billion stars in the Milky Way galaxy, and there are about 3 billion similar galaxies in the observable volume of the universe. So altogether, there are 10 to the power 20 habitable Earth-sized planets in the observable universe. So an interesting question for a statistician is it reasonable to assume that life, or intelligent life, is only realized on our planet if there are 10 to the power 20 such planets in the observable universe? Are we alone? If we want to detect the markers of biologically produced molecules, or biomarkers, in the next decade, the best instrument to use would be the James Webb Space Telescope, which is the successor to the Hubble Space Telescope. And here you see how the sunshade opens up in this illustration. We hope it will open up when the telescope is launched in October 2018. And this is the telescope. It's a 6.5 meter telescope in diameter, sensitive mostly to the infrared. And it will be in an L2 orbit around the Earth. And this would be a fantastic instrument to search for biomarkers. There are also large telescopes that are being planned and starting to be constructed right now. And in fact, Harvard is a member of the consortium that builds one of them, the Giant Magellan Telescope, that includes 7 mirrors, as you can see here. But there are 2 others. There is the 30-meter telescope, and there is the European Extremely Large Telescope that is the most ambitious of them all, 39 meters in diameter. And the best prospects for detecting biomarkers is actually not for Earth-like planets around sun-like stars, but for Earth-like planets around a white dwarf. And a white dwarf is basically what the sun will become when it dies. When the sun will consume its nuclear fuel, it will shrink in size and reach dimensions that are similar to the Earth. So imagine the sun maintaining most of its mass, but shrinking to a size similar to the Earth. Just due to the contraction, it will keep itself warm. But now, if you happen to have a planet like the Earth orbiting a star that is a white dwarf, if the planet is passing in front of it, it would block a substantial fraction of the light of that star. So that makes it much more easy to detect the signatures of biologically produced molecules in the atmosphere of that planet. So if we want to do it in the next decade, actually, searching for habitable planets around white dwarfs seems to be the best path forward. And in fact, there is a habitable zone around white dwarfs. Instead of it being at the distance of the Earth from the sun, since the white dwarf is 100 times smaller than the sun, it's roughly the size of the Earth, it turns out that within a few billion years, white dwarfs that are the most common in the galaxy, they have a surface temperature very similar to the surface temperature of the sun. So they have the same color as the sun. You just need to get 100 times closer to them in order to keep yourself warm. So the habitable zone, when the surface temperature is roughly 6,000 degrees Kelvin, the same as the surface temperature of the sun, the habitable zone is 100 times smaller in radius than the Earth-Sun distance. And that applies to a white dwarf that is a few billion years old. And as I mentioned, since the white dwarf is roughly 1% of the size of the sun, it has roughly the size of the planet. And so that's very good in terms of looking for these biomarkers. The orbital time, if you consider a habitable Earth-like planet around the white dwarf, the orbital time is only 10 hours instead of being a year, because the planet is 100 times closer to the star. And when it passes in front of it, the event lasts only 2 minutes. So you really have to monitor very carefully with a large cadence the light curve of the white dwarf. But white dwarfs are very common because the sun was born roughly 5 billion years ago. There are stars that were born earlier than the sun. Plenty of them died by now, and we can see a lot of white dwarfs in the Milky Way galaxy. But nobody searched for transiting planets around white dwarfs, so that's the next important step that one should take. And if one finds transiting planets in the habitable zone of a white dwarf, then one can look for the signature of molecular oxygen on the surface of those planets. And it turns out that with a James Webb Space Telescope, it should be possible to detect the signature of oxygen within 5 hours of total integration time. And we wrote a paper about it just a year and a half ago, suggesting that. So that opens the door within the next decade to search for molecular oxygen. What about intelligent civilizations? Well, one way to search for those is to look for industrial pollution. Now, you might say that if you find industrial pollution, it shows lack of intelligence, because these civilizations are not taking care of their planet. We don't take care of the planet. I wonder if any of you participated in the march that stated that a couple of days ago. But you could also imagine that the planet is positioned at a distance from its host star where it's too cold for life to exist. So actually, industrial pollution would be advantageous. You might want to warm up a planet that is otherwise too cold to inhabit. So can we look for the signatures of industrial pollution? And this is work done with an undergraduate, a bright undergraduate who is sitting in the audience somewhere over there, Henry Lin, over this summer. And with Gonzalez Abad, who is somewhere else, where we basically took the spectrum of the Earth's atmosphere and asked, what are the fingerprints of pollutants, molecules produced by industrial pollution? Can we look for those fingerprints with a James Webb Space Telescope? And these are just spectra where you see the fingerprints of pollutants. They are called CFCs, and there are different molecules that are being produced by the industry, especially refrigeration systems or hairspray. If these extraterrestrials are hairy, they might produce more. And we found that if the abundance is about 10 times or more than the abundance of these pollutants on Earth, then in principle, the James Webb Space Telescope could detect them for a habitable planet around the white dwarf. So that's an interesting new way of searching for industrialized life out there. And there is an interesting twist to this story, that there are different types of molecules, different types of pollutants. Some are long-lived, like, for example, CF4, carbon with 4 fluorine atoms, which survives 50,000 years. But there are other molecules that are very short-lived. So if you find evidence for the long-lived molecules, but not for the short-lived molecules, this might signal that a civilization that died by now. And it would serve as a warning sign for the risks of industrial pollution here on Earth. So here is a policy or sociological effect that detecting life elsewhere can have on our civilization. And the way to search for these pollutants is, well, first of all, you would see molecular oxygen, because it's much easier to detect in the Earth's atmosphere. Then you would find the evidence for methane and the N2O and the other molecules that are producing stronger signals. And eventually, you can find, by integrating for a longer period of time, you can set constraints on the existence of industrial pollution. And now let me move to the largest distance scale of them all, the universe at large. Is there life in the universe? Forget about our galaxy, which is 1 out of 1 trillion galaxies like it in the universe. So let's start with the past, because we also have the time domain. We can ask, when did life start in the universe? And we basically are situated at the center of an archaeological dig. I don't know if any cosmologist told you that, but you can think of the universe as an archaeological dig, spherical archaeological dig around us, quite different from conventional archaeological digs where you go down in one direction. Here, it's in all directions. The farther you look, the earlier is the time that you're seeing, because it takes light some finite amount of time to reach us. Light propagates at a finite speed. So if you're looking at a very distant source, you're seeing that source when it was much younger. If you place a mirror in front of you, you're actually not seeing the image of yourself. Right now, you're seeing the image some time ago, the time that it took light to bounce from your face to the mirror and back. So if you place the mirror light year away, you would see how you looked like 2 years ago. And when we look deep into the universe, we are seeing how things looked like very early on. And so there is a maximum distance that we can see. That's the distance that light traveled during the age of the Big Bang, during the age of the universe, since the Big Bang. And that's the depth of our archaeological dig. If we go that far, we would basically see the early beginning. And some people are trying to see signatures of those very early times in the cosmic microwave background. Some people here at Harvard, led by John Kovac. But generally speaking, there are layers around us, spherical shells. And the farther a shell is, the earlier is the cosmic time that it represents. So in principle, we can see what happened in the universe at early times. We don't need to speculate. We can just look out there, build sensitive enough telescopes, and see how the universe looked like at earlier times. It's a fantastic time machine. Of course, this is possible only because, on very large scales, the universe started from very similar initial conditions. If the initial conditions were very different at the place that is far away from us than it is here, we would never be able to conclude what happened here at earlier times. But since the universe had roughly the same initial conditions everywhere, we see that it has the same conditions in all directions and at all places. That allows us to infer how the entire universe evolved at early times. So we are situated next to a star that we call the Sun, which is 1 out of a fraction of 1 trillion stars in the galaxy. This is another galaxy, but if you were to look at the Milky Way from the side, the Sun would be roughly here. And you can ask, when did stars like the Sun form? There must have been a time when stars like the Sun or galaxies like the Milky Way did not exist, because the universe is expanding, and if you go back in time, the universe was denser and denser. And so there was a time when the universe was denser than the Sun. And a star like the Sun could not have existed back then. When and how did the first stars form? That's equivalent to searching our cosmic roots or looking for the scientific version of the story of Genesis. So it's quite remarkable that nowadays in astronomy, we can actually address questions that were previously in the realm of philosophy or religion. And we can actually do that using computer simulations. We can feed the initial conditions of the universe into a computer code that solves the laws of physics, the standard model of physics. And starting from the initial conditions, what we find, and you can see it on the left here, this is the distribution of the dark matter. What we find is that matter accumulates in sheets, and then these break into filaments, and at the intersection of filaments, matter is building up galaxies. You can see a cosmic web of galaxies building up in the universe as it ages. The clock is on the top right here. And then what you see here is the outcome at the present time if you add ordinary matter. We don't know what the dark matter is made of. That's one of the unsolved puzzles that we can ask extraterrestrials about. But the simulations that are produced these days, and this is state-of-the-art simulation produced here at Harvard, actually, make galaxies that look just like the Milky Way galaxy. They look like flattened disks that have the right dimensions that make stars just like the Milky Way galaxy. So we have great success at reproducing the observable universe from the initial conditions in the universe. And using these simulations and other tools, we can figure out when the first stars formed in the universe. So we have a theoretical picture for when the first stars formed, but observationally, there are some blank pages in this photo album of the universe that we collected so far. We have an image of the universe at very early times. This is the cosmic microwave background that was left over from the hot Big Bang phase of the universe. We can see directly at some point in time, 400,000 years after the Big Bang, the universe became transparent. So this radiation started streaming freely through it, and we can see it today. We also see galaxies at relatively late times, more than 1 billion years after the Big Bang. But when did the first stars form is a question that is not answered yet, because there are some missing pages in this photo album of the universe that we would like to fill in with images using, for example, the James Webb Space Telescope. But since the universe is expanding, if you reverse the movie backwards in time, you would realize that the universe was hotter at earlier times. And so the cosmic microwave background radiation that we see today has a temperature of only 3 degrees Kelvin, very close to absolute zero. It's freezing out there. Just because we are close to the sun, we feel relatively warm here, but it's freezing out there. However, if you go back in time to when the universe was only 15 million years, then the temperature of the cosmic microwave background was 300 degrees Kelvin, or roughly the temperature in this room. And it was very comfortable for life to exist back then. It so happens that the first stars formed just around that time. So in a paper that I wrote less than a year ago, I just pointed this out. And it was a very short paper that I wrote over Thanksgiving. The idea occurred to me in the shower. That's usually the place where I have peace and quiet. Nobody bothers me. And so I don't get any emails. I can think about things. And it just occurred to me that there was this early time. Then it was Thanksgiving Day, and I asked my wife if it's possible for me to wash the dishes after the guests arrive, because I want to write this paper before they arrive, and she allowed me. So fortunately, I was able to get it done. And even though this is a very simple idea, a very short paper, for some reason it captured the imagination of a lot of people and got a huge media coverage that some of my colleagues think it doesn't deserve. But one interesting conclusion from this is that life could have started in the universe much earlier than the present time. And so there are cosmologists that argue that the values of the cosmological parameters that we observe today must have been this way so that we would exist on the surface of a planet like the Earth, around a star like the Sun, in the Milky Way galaxy. But that may not be the case. Life could have started much earlier. And if that's the case, then the universe was not designed in order for us to exist in it. We're just a byproduct We exist today. Life existed earlier. It's not a big deal. Shouldn't interpret the parameters of the universe as being responsible for our existence. And actually, quite serious people use this argument. I'm talking people that have tenure position at major institutions. This is the dominant paradigm among some communities of particle physicists, which I find mind-boggling. Because in principle, the universe could have started to have life in it when the density of matter was 1,000,000 times bigger than it is today. And so the fact that the universe is dominated by a cosmological constant today has nothing to do. I mean, it's true, the Milky Way galaxy formed just now. We exist now when the cosmological constant has roughly the matter density. But if life could have started much earlier, then you have 6 orders of magnitude of range where life could have existed. This is called the anthropic argument, and you may have heard a lot about it from other people. Now, of course, if life forms in some special locations, the question is, can it be transferred? Can it be transported? And a proof of concept exists with small animals, tiny animals that are called tardigrades. They sort of look like tiny bears. I mean, if you look at them with a microscope. They were discovered in 1773 by Goethe. They have a size of a fraction of a millimeter. They sort of look like bears. And they are very resilient. In 2007, a group of tardigrades were launched into space for 10 days. And they were exposed to extreme dehydration, vacuum, freezing temperatures, weightlessness, and bombardment by damaging ultraviolet radiation and cosmic rays. And then they were brought back to Earth. A substantial fraction of them survived and gave birth to viable embryos. That's quite remarkable. These are astronauts without a helmet. They were put out there, and they survived. And one possible explanation is that they have a self-repairing DNA. Surprisingly, the DNA of these animals was never investigated in full detail. And in fact, work on this frontier is done here at Harvard by Professor Lemos. So in principle, you can transfer forms of life under extreme conditions from a place where they exist to other places. You might ask, what would be the vehicle by which life would be transported? So you can think, if it's intelligent life, you can imagine launching spaceships that will target other planets. But there are also natural processes. For example, when 2 galaxies come together, usually they have central black holes. These black holes are surrounded by stars. And then when they form a binary system, the 2 black holes move around each other, you can have a slingshot effect, where a star gets thrown out of the system of this binary black hole system. So this is work in progress that we have done with James Guillochon here at Harvard, where we found that such a process can produce stars moving close to the speed of light. You can eject stars up to a speed that is close to the speed of light from galaxies, and these ejected stars could, in principle, transfer life from one galaxy to another. What about the future? Will life survive in the universe in the distant future? So over a decade ago, about 13 years ago, after it was realized that the universe is not just expanding, but actually its expansion is speeding up. So in fact, if you look at a galaxy far away, it's receding away from us, but in the future it will recede away from us even faster and faster, eventually reaching the speed of light. So what does that mean? I thought about what the implications might be, and I wrote, again, a short paper after thinking about it in the shower. This is a repeating theme in my short papers. And what you realize is that every distant source that is following the cosmic expansion will eventually run away from us at a speed greater than the speed of light. And once it reaches the speed of light, after that time, you won't be able to receive signals from that source, because even light will not be able to bridge the gap that is being opened between the source and us at an ever-increasing speed. So that means that we have a finite amount of time for every source we see on the sky during which we can detect signals. So if there is an extraterrestrial friend on a galaxy far away, we will not be able to communicate with that extraterrestrial in the distant future, because eventually there will be no cell phone communication. Even particles of light will not be able to travel from that source to us. And you can sort of understand it by using an analogy of a balloon. Think of the balloon as expanding space, and think of photons, the particles of light, as ants walking on that surface. So the ants are moving at a finite speed. The photons are moving at the speed of light. But the balloon, in principle, can expand faster than that, so that the area visited by an ant would be limited on the surface of the balloon. There is a region that is much smaller than the size of the entire balloon that the ants can visit if the balloon is expanding fast enough. And so that's, in the context of photons in our universe, that is called our horizon. There is a horizon out to which we can see things, but if space is expanding too fast, then galaxies will exit from that horizon. We won't be able to see them after a while. So you can ask, how many galaxies will reside within our horizon in 100 billion years? And the answer is, just to remind you, the universe, the age of the universe today is 13.8 billion years. So I'm talking about the time when the universe will age by roughly a factor of 10, 10 times older than it is today. At that time, there will be only one galaxy that is visible to us, our own galaxy, nothing else. And actually, it will not really be the Milky Way galaxy as we know it. It will be the merger remnant of the Milky Way and its sister galaxy, Andromeda. So the two galaxies are about to collide. And in a paper that we wrote with a postdoc here, I decided to call the merger product of the two galaxies Milkomeda. So it's the merger between the Milky Way and Andromeda. And it's the only cosmological object that will be observable to us in 100 billion years. The collision will take place during the life of the sun, within the next 5 billion years. And the night sky will change once the two galaxies come together. So we actually simulated this with a computer. And this is the only paper of mine that has a chance of being cited in 5 billion years. So here you see the Milky Way and Andromeda coming together. And here you see the simulation, including the gas on the left and the stars on the right. And the two galaxies will smash into each other, creating eventually a spherically looking, a spheroidal galaxy called an elliptical galaxy out of the two disks that smash into each other. It's interesting to ask what will happen to the sun during this process. So if you imagine a lot of sun-like stars at the distance of the sun from the center of the Milky Way, and then as Andromeda passes by, within 2 billion years, these stars will be tossed around, and in fact, they will spread. There are some stars that are captured by Andromeda, so in fact, there is a chance that the sun will be captured by Andromeda before the final merger, and then we will see the Milky Way from a distance. And by the way, when Andromeda comes close, we would see it as big on the sky as the Milky Way is. We would basically see two strips of stars on the sky. That would be quite amazing in a few billion years. And then eventually, when the two galaxies come together, the sun will most likely be displaced out away from the center of the merger product than it is today. So you may ask, okay, Milkomeda is the only galaxy that we will be able to see in the distant future. Will there be life in 1 trillion years? That's when the universe will age by a factor of 100 relative to its age today. Well, it's actually possible because stars that are a tenth of the mass of the sun, these are called dwarf stars, they are the most abundant around us. There are many more such stars, almost 10 times more such stars than sun-like stars in the vicinity of the sun. They have a lifetime of 7 trillion years. So when you make a star much smaller, it's much fainter and it lasts for a much longer time. You can think of a star as a nuclear plant that burns nuclear fuel. And if you burn the nuclear fuel slowly, it will survive for a longer time, even though the fuel reservoir is smaller in a low-mass star. So a tenth of the mass of the sun will shine for 7 trillion years. We can simply move to such a common star in our vicinity and live next to it, just a little bit closer than we are to the sun so that we will be warm enough. And then we can think, oh, well, will our descendants be able to study cosmology, study the universe? So you can imagine the President of the United States making the State of, instead of the Union, the State of the Universe address. And there are two parts to this. Well, if you think about the situation today, cosmologists are trying to explore the scientific version of the story of Genesis, as I mentioned, trying to look back in time, figure out when the first light was produced. Let there be light. So religious ideas are now, about Genesis, are now being modified by science. But if you think about the future, the merger product of the Milky Way and Andromeda, in other words, Milkomeda, will be the only galaxy that is visible to us when the universe will age by a factor of 10 or more. And subsequent generations of observers will not be able to find evidence for the Big Bang because they will not be able to see anything beyond Milkomeda. You can ask this question, will cosmology turn into a religion at that point? Because there would be books telling us a story that we won't be able to verify. In fact, once the universe will age by a factor of 100, the wavelength of the cosmic microwave background will be stretched to dimensions that are as big as the horizon of the universe. So there would be no meaning to talking about the cosmic microwave background because there is no photon, even one photon, in the universe at that late time. The wavelength is as big as the entire horizon. And that's simply due to the exponential expansion of an accelerating universe. So there would be no trace of the Big Bang at that time. Once again, I was troubled by this. And actually, this time it was a very snowy day here. And so classes were canceled, and I had to stay home. That was one of the rare days where Harvard was closed. Never happened in a long time. But that allowed me to think about this question. And I wrote a short paper suggesting that, in fact, people will be able to do cosmology in 1 trillion years. And that's just thanks to stars that are being ejected from Milkomeda. As I mentioned before, there are hypervelocity stars ejected from galaxies. And even if you have a single black hole, you get those ejected because you can have two stars passing close to the black hole, getting ripped apart. One of them flies far away, the other one stays bound. And so in principle, you can use these stars that are flying out of Milkomeda to trace the cosmic expansion. You can see them receding away from us and accelerating, just like Hubble used galaxies to monitor the cosmic expansion. Here you will use fast stars to monitor the cosmic expansion. So there is hope for cosmology in the distant future, at least a few trillion years from now, but not much beyond that. So let me summarize. If we start with the distance scale of the solar system, city lights, or if you think of a spaceship passing through the solar system, city lights can be detected out to the edge of the solar system with existing telescopes. The signatures of molecular oxygen informing us about primitive forms of life, or pollutants informing us of intelligent civilizations can be detected over the next decade with the James Webb Space Telescope for Earth-like planets orbiting in the habitable zone of white dwarf stars. And the traditional way of searching for intelligent life using radio telescopes can be pursued also into the future. It's important that this will continue because we never know what type of a signal we might be finding. And so we should search over a wider frequency range, a different time domain. We can search directly systems that have habitable planets around them. And life may have started very early in the universe. In principle, we could face a Copernican revolution in the context of the biological universe. Universe may have life everywhere. Life may have started early. We are not at the center of the stage in the context of life. Thank you.
So I think it's a good argument for the National Science Foundation that we have to do it now or it'll never be done. Everybody who wants to leave, leave, and then questions for the wonderful speaker, Avi Loeb. Do you want to just wait just a second? Because there's some people who have to go do homework. Oh, is Cedar leaving? Oh, so sad.
Now?
Sorry, we have one.
Can I ask now?
Yeah.
Do you have any basis to believe that in 100 billion years, the universe would still be exponentially expanding as we observe today?
That's a very good question. I was adopting the standard we have a standard cosmological model by now that includes cold dark matter and a cosmological constant. This is the standard model. If you have a cosmological constant, the exponential expansion will continue forever. This is actually the model. Having a constant vacuum energy density is the model favored, for example, by string theorists, because the energy scale that we are talking about is extremely small compared to the Planck scale. So if you imagine the vacuum having different possible values for their energy density, you just get stuck in one of these minima, and it's very difficult to excite the vacuum away from that minima. So if you ask a physicist, he or she will tell you that it's most likely that it's a constant. The other argument would be to say, well, it was fine-tuned, or at least it's unusual to find it at a value that is so small compared to the Planck scale. And then if you want it to evolve on a timescale comparable to the age of the universe, that requires a second coincidence, okay? Although it's intellectually possible, there are constraints on it already. And the most likely situation is that we have really a cosmological constant. Now, the question is, will it stay constant for 100 e-folds or not, is unanswered at the moment. But just the standard paradigm would predict that what I described will happen.
Secondly, due to the inflation in the beginning of the universe, there may already be regions that are far away from each other in the universe that are separated by distance so enormous that it will require the signal traveling at greater than the speed of light to contact each other. So in other words, there may well be life in remote parts of the universe. We just are forever unable to contact them because of the limitation on the speed of light.
That's true. That's true. So the universe went, the conventional picture is the universe went through accelerated expansion at two epochs, very early on during the epoch of inflation. But fortunately, inflation ended. And so the universe that made galaxies could have emerged out of those initial conditions. And now it's accelerating again. Maybe that will end, as you alluded to, but we don't know. And indeed, there could be vast regions of space to which we have no access, where life may exist.
Yes.
Hello.
Yes.
If there are intelligent up there, and they are probably looking at us too, and their intelligence many million years more advanced than us, and by the method you described, if it's correct, they may already found us a long time ago. But the fact that we don't see any extra intelligence ever visit Earth or left any sign or give us any signal that they found us, does that mean interstellar travel or communication is impossible?
No, it may mean that they don't care much about us. So when you walk down the street, for example, if you ever look down at the pavement, there are ants walking, right? And you don't pay attention to them. You just walk around because they look like primitive life. You don't really care about those. So, you know, they must, in principle, they might be advanced enough not to care about us. We tend to think that we are important, but we might not be in the big scheme of things. I mean, they might think of us just like we think about bacteria or algae that, you know, exist, but who cares, you know?
But maybe one intelligence not care, but all of them not care about us. But then what's the purpose of we found? If we found them, what do we do? We just found them. We don't. No, do we want to do something if we found something?
I think we should not make assumptions. We should just explore. So when Columbus went to search for the West Indies and discovered America, you know, that was an exciting discovery for him. If he were to say, well, let's think about it, is it really worth it? He would never discover anything. And I think we should just explore. Most of the time, we will not find anything. But when we do find it, will have a huge impact on progress. And it's the nature of venture capital investments, which I'm advocating in the context of science. In venture capitalism, you put some of your resources, a small fraction, I'm not saying all, but a small fraction, into risky propositions. Why? I mean, even businesses do that. Why do they do that? I mean, most of these projects do not produce anything, do not lead to successful results. They do that because if one of them succeeds, it basically justifies the entire endeavor. So and you can see that in the context of science. You know, there are lots of scientists that become dead wood at late in their career. They don't produce much science. They get funded, they get respected, they get prizes, but it's just not significant, right, what they're doing. But then every now and then you get someone like Einstein, okay, that comes up with very deep insights, and that justifies the entire endeavor, okay? So the idea is we should not be deterred by failures. Failure is part of scientific discovery. We should put a small fraction of our resources in terms of time, in terms of funds, into risky searches, risky proposition, exploration, without telling ourselves what the answer is in advance. The biggest mistake we can make is basically say, I know what I will find, therefore there is no point in doing that. That's basically a self-fulfilling prophecy.
My question is, you talked about looking for life around white dwarf stars, but I think I remember reading somewhere that they emit a lot of X-rays. Wouldn't that make it impossible for life to survive on a planet that close to a white dwarf star?
They emit X-rays if matter is falling onto them. And it's true that every now and then, so you might ask a preliminary question, how can there be planets so close to a white dwarf to be habitable? Because after all, there used to be a star, like the sun, that is much bigger than the habitable zone of the planets around the white dwarf. And it turns out that white dwarfs, I mean, there is plenty of data, white dwarfs show evidence for debris disks, where there is evidence for planetary material around them. There is also evidence for planetary debris on their surface. So when material falls onto the surface, when an asteroid gets, for example, ripped apart due to the gravitational tide exerted on it by the white dwarf, then the material rains on the surface of the white dwarf, and you can see it, evidence for it. And people have found that a quarter of all white dwarfs show evidence for that. So indeed, when the material is raining on the white dwarf, you get X-rays. But during quiet periods of time, when there is no accretion, then you could, in principle, have a planet next to a white dwarf. And right now, we don't know the answer. We have to, I think, search for planets orbiting white dwarfs. And in fact, there are various techniques, one of which we suggested with Henry Lin very recently, to look for orbiting objects around white dwarfs.
So my question regards sort of the last point and the length of time it takes for the universe to become habitable. And another ingredient in life and planets are the heavy elements, or metals as astronomers call them, that are produced in stars and distributed by supernovas. And this process takes some amount of time to build up enough heavy elements to make planets and life. So how long of a length of time does that kind of take in order to produce habitable conditions?
That's a very good question. So the point is that on average, indeed, the metal abundance in galaxies grows with time because you keep building up the metallicity of galaxies as time goes on. But if you imagine a supernova exploding in some region of the interstellar medium, the region enriched by the supernova has a very high metallicity, even if this is a supernova resulting from the first generation of stars. So there would be always pockets where the enrichment is very high, starting from the beginning. It's a mistake by many astronomers to think that when you consider early stars, they should have had low metallicities. This mistake assumes that the mixing is very effective, that you basically mix the heavy elements with all the gas that you have. But in fact, there are pockets where the metallicity could be very high, just very early on, and early generations of stars and planetary systems will already have those metals in them.
Even in a few million years?
Massive stars can explode, have a lifetime of a few million years. And, it's within the age of the universe at those early times.
Yeah. Are you next?
For us, we live around a star that's amazingly stable. The sun only varies by about 0.1%. We're in a nearly perfect circular orbit around the sun. So the temperature on the Earth, actually, other than anthropogenic factors, is very stable. But you just talked about tardigrade, which could have huge tolerance. As we look for intelligent life, how much tolerance should we give to the variability of stars, which most of the stars are variable and they have a variability far greater than the sun?
Well, that's a very good question. If we look at the history of mankind, humankind, the living conditions were pretty poor early on. It's much better now. And we were able to adjust. But you're right that if the temperature variations were much larger, then probably our species would have been extinct. And I think we know very little about this. We know very little about the origins of life, not to speak about how you make big mammals out of single-cell organisms. One way to approach your question would be to do laboratory experiments. And some people, for example, Jack Szostak here at Harvard, are trying to create life in the laboratory. If you can create life in the laboratory, then you can examine the sensitivity of life in different forms to conditions, to external conditions. I should mention that these studies are not just interesting academically because they might lead to improved medicine, to a better understanding of how life operates, not only how it started, but how it operates. And it's not just that this field is interdisciplinary. It will have important implications. Better understanding of how life forms will have important implications for improving our quality of life, I think, in the distant future, if we use it wisely.
Has anyone speculated that alien planets could have completely different biochemistries and so would actually produce different chemistry, might not produce primitive molecular oxygen, but something completely different? And will that be able to be detected as well?
So the most common assumption is that you need a rocky planet. You need a hard surface on which you can concentrate. So if you have liquid water and you evaporate the water, you can concentrate the molecules and allow them to interact more effectively. If you don't have a hard surface, it's difficult to concentrate molecular concentrations. Nevertheless, back in the 70s, Carl Sagan suggested maybe life could exist in ammonia or other forms of liquid. I think we have such a poor understanding of how life started in liquid water that right now, not many people are examining, actually, the possibility in other liquids and in other forms. In my view, in principle, life could be very diverse. We might have conditions for life as we know it here on Earth, but in other environments, it might be quite different. And that actually begs the question of whether we can identify its existence, because if we are looking for life like that is similar to us, we might not find it as easily if we don't know what to look for. Yeah. I should mention that when neutron stars were discovered, these were discovered as pulsars, beacons of light basically sweeping through space. And when people found them, they thought that little green men are producing them. Then they realized that it could be due to a star as massive as the sun, but with a radius the size of Boston. These are called neutron stars that were predicted earlier, that is spinning around, and if the rotation axis is not aligned with the beam of radiation that it's emitting, then you would get a lighthouse effect. And every now and then we discover new phenomena. So for example, a couple of months ago, I had an exchange with Jill Tarter, that used to be the director of the SETI Institute. There is a new class of sources called fast radio bursts. Nobody knows where they come from, and she conjectured that maybe they come from extraterrestrials. But based on various arguments, I argued otherwise. So whenever a new phenomena is discovered, people think maybe, but so far none of them seem to be a robust case.
So I appreciated, as someone aspiring to do science, when you related how you get inspired by showering. And I hope we should not conclude from that if you ever stop publishing short papers, you will have stopped showering.
No, I think the biggest risk is that I will have too many administrative duties, and that would lower my productivity. That's the only risk.
Okay. I have a more serious question as well, though. You mentioned that at some point the wavelength of the CMB will exceed the causal horizon, and we won't be able to measure those photons. But have you considered the sort of Boltzmann tail of the CMB, the higher energy photons that will perhaps be redshifted? Now, of course, there are fewer of them, but presumably alien or future human civilizations will have much more sensitive technology as well.
Right, but the point is, since the universe is expanding exponentially, then you're running out of photons fairly quickly. So in fact, soon after the time that I mentioned, even the higher energy photons are not observable. The point is that when the wavelength of a photon is as big as the horizon of the universe, you can't build an instrument, even in principle, that would detect it as a photon, because a photon is a time-dependent electromagnetic signal. And here you will just see a constant, a DC, electric or magnetic field throughout the entire universe.
I think you're underestimating experimentalists. but that was a great talk. Can we thank Avi again for this wonderful talk?